discovery that shook the world. What happened?
Well, what happened? Two black holes collided a long, long time ago. And the amazing thing is that no humans existed when black holes collided. But while the waves traveled through the universe, Homo sapiens developed on Earth, and by the time the waves reached the Earth, we not only existed, but had developed instruments which were sufficiently sensitive to detect this tiny, tiny vibration of Earth when the gravitational wave swept past.
Where was it? Where was the collision?
Oh, the collision was 400 megaparsec away. We don't know which galaxy it was exactly, but we know that it was 1.3 billion light years away, which is quite far away. But it's very difficult to pinpoint the location exactly because the detectors we have are not very sensitive directionally. So they can point to an arc on the sky where it might have happened, but cannot say exactly that this was where it was.
Could it happen closer to us?
It could happen closer to us. It might happen closer to us in the near future, but we're getting so few gravitational waves at this time that I cannot tell you when we'll see something which is even closer.
Would this be like dangerous for us on the Earth?
This will probably not be dangerous for us unless Earth would collide with a black hole, which is not going to happen anytime soon. But the effect is so tremendously small. And here we're talking about trillionths of a millimeter on a length which is the size of the diameter of the Earth. That this is not something which an ordinary human would even feel. This is why we need these extremely sensitive instruments.
So even when they arrived at Earth, nobody could feel it.
That's right.
Although they went just through us.
So we believe that there are gravitational waves sweeping through the Earth all the time. Now even. And if we're lucky and the amplitude is slightly larger, then we are able to detect them. But mostly we are not even able to see them.
What was this sound of the gravitational wave like?
Oh, so the point is, and I want to stress that gravitational waves are not sound. But the waveform has wiggles in them. And if you look at these wiggles and how they vary over time, you can represent what you see in terms of an audible signal. And this was the chirp we just heard. So it so happens that the frequency of these waveforms is almost the range of human hearing. And this is why we're saying that the gravitational waves are loud, that we can hear them.
So what was the main achievement of this year's laureates?
Well, so their competencies are quite complementary. Rainer Weiss is the founder of the whole project. He developed the concept starting in the beginning or the middle of the 1960s. He built the first prototype detectors in 1967, and then he demonstrated the principle. He charted the various noise sources which would influence the performance of the detector. And as I've been trying to mention, the detector is incredibly sensitive. A truck passing by will make the detector vibrate. Ocean waves some distance away make also the detector vibrate, seismology, other things. So you have to know very, very well what kind of sources can give you signals which simulate gravitational waves to be able to distinguish the true from the false. So his main influence on the project is developing a prototype, charting all the sources of disturbances, and finding means to offset these sources. Thorne is this inspiring theorist who figured out what kind of signals you can expect from astrophysical sources of these waves. So what to look for, how sensitive does the instrument have to be able to observe what the universe behaves like in terms of gravitational waves. And then we have Barry Barish, who is the person who joined the experiment late. He only arrived on the scene in 1994. However, he is the visionary behind upgrading the sensitivity of the instrument to the level where this detection was possible. The original LIGO could not have made the detection, which was possible thanks to the development initiated by Barry Barish.
So the other two worked like for 50 years with this project. What did they say when they got the call from Stockholm this morning?
Well, I think they were expecting it, more or less. As I said at the press conference, the first discovery of a gravitational wave, the first direct measurement, caused a sensation worldwide. So it's been speculated already for a year that this was a deserving discovery. And so I think they were half expecting it. They were still humbled and very, very gratified that they were awarded the prize, but also all three of them mentioned, one, that they were happy that they were not alone, and two, that we should make sure to stress the role of the collaboration at the press conference and even at the award ceremony.
So how was this collaboration? The LIGO collaboration?
Yes, the LIGO collaboration has grown over the last 40 years. In the beginning it was small, it was just groups at MIT and at Caltech, at the universities in the United States. But then as the detector grew in size and people started talking of kilometer-long arms, the collaboration also grew, and groups joined all across the United States, but also in Europe and in Australia. So today, the LIGO collaboration consists of scientists at 90 universities all across the world.
So you are like going to invite to Stockholm like 1,000 scientists?
I would like to. Unfortunately, I don't think it is possible, but each Nobel laureate has the opportunity of inviting a certain number of people, so I hope that we'll get representatives from across the collaboration.
So now when the gravitational waves are here, in some sense, what will they tell us about the universe?
So what we hope to learn from the gravitational waves is, one, about black holes and about gravity in its strong regime. You have to imagine gravity as the weakest force we know of. It's much weaker than electromagnetism. Just think of a kitchen magnet, a small magnet you put on the door of your fridge. It stays up, it doesn't fall to the ground, which just shows you that electromagnetism is much stronger than gravity. So the gravity forces we know of from the Earth are weak. Gravitational forces close to black holes are extremely strong. So the discovery of gravitational waves carrying information from the surroundings of black holes will teach us something about the strong regime of gravity, which is very, very exciting. We'll learn something about violent explosions, like supernovae or gamma ray bursts. We might learn something about the Big Bang, because the Big Bang left imprint on the universe in terms of gravitational waves, which we've never seen before. They're even weaker than those which have been observed previously. But even more exciting, there are parts of the universe which are dark, which we've never seen before, because electromagnetic radiation doesn't reach us from there. Gravitational waves are unstoppable, so they will. So we hope to learn about this dark universe.
Thank you very much, Olga Botner, for taking your time with us.